All right, so we ended last time. We ended last time by talking about Newton's second law, and then how to solve or how to implement Newton's second law for some of these types of problems. We're going to go into more detail, but go to the quiz, go to the past quizzes channel if you want to talk about quizzes. But wait until everybody's done taking the quiz, so wait until 11:45. Right, so today we're actually going to, so let me summarize. So we went over Newton's three laws yesterday, or Monday, Newton's first law, second law, and third law, and outlined what they mean, what forces are, and so on. So before we can actually continue to use them, I mean, we can use them to an extent, but before we can do that, it would be super useful to actually go over some specifics of forces, like what they are, how we calculate with them, and so on. So we're going to do that. So we've already more or less talked about gravity. You guys already know the gravitational acceleration is A, so you already know that the gravitational force is mg. Sorry, the gravitational acceleration is g, so the gravitational force, at least its magnitude, is mg. But there's a little bit more to talk about with regards to gravity. So let's talk about specifics of forces. And let's start with gravity. So you already know the basics about gravity. But you might still have the question of why heavier objects, I'm going to put heavier in quotes, seem to fall faster than lighter objects. So you guys already might know the answer to this, but let's go through a thought experiment and try to understand mathematically why this happens. So let's first consider two identical objects, identical in every way, except their mass is different. So you have two identically shaped objects, identically colored objects, and all of that. But one has a large mass, one has a small mass. And so one way that you could do this, if you wanted to run this experiment for realsies, is you could make one of your objects out of, say, plastic and another one out of, say, steel or something. So they have the same size and the same shape, but one would be have significantly more mass. So we know right off the bat from our intuition that the acceleration that the lighter one will feel will be less than the acceleration that the heavier one, sorry, not the acceleration that it'll feel, the acceleration it will experience. And so the question is why? Well, so what we can do is we can handle this or we can examine this setup by using a free body diagram. And we would note that on each of these things, there are two forces. There's the force of gravity downwards, and then there's a drag force upwards. So those are the only two forces present in the real world, or those would be the only two forces present in this scenario. So why don't we do a calculation then? So first, let's start off by just writing out that, so we know that the force of gravity divided by the mass of the thing that it's acting on is equal to g, right? That's just a true statement. That's what it means for the acceleration due to gravity to be g. And we know that in the real world, when drag is present, the acceleration of any object will be less than g. So in particular, the acceleration of the heavy object will be less than g. So we can use this free body diagram over here to write out what that acceleration would be. We would add up the forces in the various directions, and then we would divide by the mass. Now, implicitly, I'm assuming g is positive here, so I'm assuming that this is the plus y direction, and there's nothing in the x direction, so we don't have to worry about that. So what would the net force then in the plus y direction would be F sub g of the heavy object minus the force of the drag divided by the mass of the heavy object. So what I'm doing is I'm computing the component of the force in the plus y direction. So the force of gravity contributes plus F sub g sub heavy in the y direction. The force of gravity contributes minus F sub drag in the plus y direction, because it's pointing in the opposite of the plus y direction. So these are really components of vectors, but this is a one-dimensional problem, so we can just use pluses and minuses. Now, importantly, we know that well, how do I want to phrase this? We know that this is supposed to be greater than the acceleration of the light object, right? That's just what our intuition tells us, that the acceleration of the heavy object is greater than the acceleration of the light object. But the acceleration of the light object is equal to f sub g of the light object minus f sub drag divided by the mass of the light object. So we can do some quick simplifications. We know that the force of gravity divided by the mass, that's just g. So what do we get? We get that the acceleration of the heavy object is g minus the force of drag divided by m sub heavy. And the acceleration of the lighter object, this is the downward acceleration, by the way, acceleration in the plus y direction using this coordinate choice, is g, because we have this f sub g over m light, minus f sub drag over m light. So then we can compare. So the fact that a heavy is greater than a light indicates that f drag over m heavy is less than f drag over m light. And of course that's true. There's a caveat here. You have to know in advance that the drag force doesn't depend on the mass. But that your intuition should agree with that. Drag force, and this is a true statement, drag force really only depends on the shape and the size of the object that it's affecting. Like if you have a very sleek object, it'll experience less drag than if you have like just a brick. But it doesn't actually depend on how much the thing weighs, how much mass it has. It just depends on the shape and the size. So if these two things, the forces of drag on each of the objects are the same, and I've used the same variable to represent them, then of course this term is less than this term, and that has to be the case because the numerators are the same, but the denominators are different. So to answer the question, why does the heavier object accelerate more? Well, the effect, they experience the same gravitational, they experience the same contribution to their acceleration from gravity, but the negative contribution to the acceleration from the drag is smaller for the heavy object. And that's because the forces between the two objects are the same, but the masses are different. So the reason why a feather falls much more slowly than a brick is not because drag and air resistance are the same thing, is not because one has a harder pull of gravity on it or something like that. It's because the feather weighs significantly less than or has significantly less mass, but a comparable drag force. And so that drag force will have a larger effect on its acceleration because it has less mass. No, so usually, well, I guess you could use d, but I never really will. I'll usually just write f drag because we don't use drag a whole lot anyway. So there is a consequence here. You said it's because the negative contribution of the drag force is less. Yeah, so the acceleration is composed of is the sum of two terms. There's the g that they both have. They both have g here. And then there's also the negative contribution, which slows down its acceleration in both terms. And the point is the amount that the drag, the negative contribution, contributes to the heavy acceleration is smaller because it has a larger mass. And the amount it contributes to the acceleration is inversely proportional to the mass. That gets to a separate issue. We can talk about that after lecture, though. It's a good question. So there's just a simple consequence here, which you guys probably already know. If there's no drag, the force of gravity is equal to ma, where a is equal to the gravitational acceleration. And so what we can do is we can just say that the force of gravity is just always equal to mg. The force of gravity acting, or the force of gravity on Earth anyway, acting on a body is mg. Now this is a magnitude. Remember, forces are vectors, but this is the magnitude. Notice I did not draw a little arrow over it. So this is just the magnitude of the force. You'd have to figure out the direction depending on what your coordinate system is. But this is a good thing to remember. Whenever you have an object that is experiencing gravity on your free body diagram, you should make sure to include a downward facing arrow with magnitude mg. Now, one thing I don't want to see is I don't want to see this. That's sloppy. Better would be to do this, and then later on say Fg is equal to mg. That's like, it's not an issue of right versus wrong, because as long as you know what you're doing, it's fine. But it's just sloppy because it indicates that you're not really taking into account the vectorial nature of the force. So just keep that in mind. Right. Okay. The next force to talk about is tension. So tension is the force. Do we need to include? No. I mean, yes. I mean, you don't have to. Like, it's just for you. It's not for me. Tension is a force that comes about, it's a pulling force that comes about from like chains and ropes being tied to things and being pulled on, right? So usually, for the sake of this class, but we will drop this assumption later, usually we assume that the rope is massless. We assume that we have a massless rope or a massless chain or whatever. That's just, it makes our calculations easier. So the reason why we do that is because if we didn't, then it introduces a lot of complexity to the calculations that we don't really need to focus on. Because for the most part, if you have like a climbing rope, the climbing rope's mass is negligible compared to the things that you're hoisting with the climbing rope, right? Because the rope can generally hold a lot more tension than the mass might otherwise indicate. So we can just assume it's small and negligible. Now, the reason why we like tension, the reason why tension is useful to begin with from a mechanical perspective, is it allows us to use rope. And when I say rope, that also includes chains and so on. It allows us to use ropes and string as a conduit. And I'm going to put conduit in quotes here because it's not explicitly a conduit, but it's a conduit to separate third law force pairs by a distance. So what I mean by that is, for example, let's say that I have one block here and another block attached to a rope. If this block is experiencing, let's say this block is, do we need to, oh, okay. So the point is that if these two blocks were glued together, and then this block was the left block was being pulled, then it would apply a force to the right block because of the glue, right? It would pull the right block along with it. And so the right block would pull the left block back, equal and opposite forces and all that. What a rope allows us to do is it allows us to distribute that across the rope. So this block might experience a force to the left. And so this block pulls on the rope. So I'll draw a little arrow there, pulls on the rope to the left. And so the rope pulls on the block back. But if the rope is but if that tension force is being that tension force is uniform across the rope, then this rope will pull on this block forward. It's so hard to explain without using an example. The point I'm trying to get at is that typically when two things are attached, if one object starts moving, it'll apply a force to the other object, and then there will be a third law force pair. All a rope does is it allows you to transmit that force as if they were connected, even if they're separated, as long as they're connected by a rope. Now, ropes don't really work when you push on them; they only work when you pull. But the point is ropes transmit force without changing it. That's a useful fact. So I'm actually just gonna give a quick example rather than trying to explain this. So explain this abstractly. So the important part that I wanted to mention, exactly, it's like the transitive property. Thank you. So when we use ropes as a conduit to separate these third law pairs, it's not always the case that the third law pairs are equal and opposite anymore. They're always equal in magnitude, but they're not always opposite, and that's important. The pair partners, and I'll draw you an example for this. And the way that this can happen is with pulleys. In analogous, the block pulling the other block, even though they're not technically contact. Yeah, it's precisely that. So typically, if the two things were connected, you would have a contact force between them. But the rope acts as a conduit for that contact force. So the example here is you might have a block attached to a rope, and then there's like a pulley attached to another rope. So in this case, you would have a tension force pulling this rope up. The third law of force pairs. Third law. Force pairs. Sorry. What does the word after say? After the say. Oh, it says pairs. You guys said that my handwriting was okay. The pairs are not always opposite. So there'd be a force of gravity downwards on this one. Now there would be a force of tension up because the rope is pulling up on the rope, or sorry, on the block. And then this block would experience a force to the right, which would also be tension. And so these two forces, these are third law force pairs, or third law partners. And so that's what I mean as a conduit, because they're not actually touching each other. They're just connected by a rope. And the reason this happens is because the tension in a rope is constant as long as it's massless, or as long as it's uniform, actually. So the whole point is that these two objects can have their third law force pairs be not opposite, even though they're still equal in magnitude. And the point is because if there's a tension on the bottom part of the rope, there has to be that same tension on the top part of the rope, on all parts of the rope. And so in particular, there would be a tension on the other side. And we'll get to examples with this, I promise. It can be tricky without actually seeing explicit examples. So just as an aside, for now, we're going to idealize pulleys. Like we do ropes. So we're going to assume that pulleys are massless and frictionless and all that business. The proper way to handle these kinds of things, by the way, is that is by considering the rope as a separate object. So T and FG is no. So T and FG are not third law force pairs because they're acting on the same body. It's remember the third law force pair between okay, so this I'll actually go into more detail here to explain this. So let's look at this example in more detail. So there's actually three objects here, right? So there are three objects. There's block one. There's block two. And then there's the rope. So the rope actually, despite it not having mass, we could draw a force diagram for it. So this is block one, this is block two, and this is the rope, of course. So let's start with block two. So there'd be a force of gravity downwards. And we know that there will be a tension force upwards. Now, why is there a tension force upwards? Well, basically, the rope is not moving, or it might be moving, but it might be moving less. So the rope is the thing that acts to pull the block up. If it wasn't there, the block would just fall. So we know that there's going to be a tension force upwards. By the way, we will often abbreviate tension force with just a capital T. Now, that tension force is really just a contact force between this end of the rope and the block, right? So if we want it to be exactly precise, this force could be described as the tension force on the block by the rope. The third law force partner, or force pair partner rather, for that force would be the tension force on the rope by the block. So there would be a downwards tension force here. Now, the point is that the the tension is equally spread throughout the rope. So there would be another, so whatever force there is, there'd have to be another tension force on the other side pulling in the other direction. You can think of it as if you pull on a rope in one direction and hold the other one still, the other one is also being pulled on in the opposite direction to keep it still, right? Otherwise, this force would force the other side to move. So these two forces are just equal, but they're pointing in different directions. They are not force pairs. They're just equal, or they're just equal in magnitude anyway. But then this force is a contact force between the first block and it. So that would have a third law force pair with the first block. So these two forces are third law force pairs. Let me be a little bit more explicit. So really it's a contact force between the end of the rope and the block, but we'll often just call it a tension force anytime a rope is involved. So the point of this whole business, the reason why I drew this diagram, is that you can see that this force on block 2 is third law force pairs with this force on the bottom of the rope, but that force has the same magnitude as the force on the other end of the rope, which is a force pair with the tension force on the first block. So what's happening is that this tension force is being transmitted all the way, sorry, this diagram's getting messy, all the way to the other block. Yeah, third law partners have to act on different objects. So the point is that the magnitudes of these two tension forces have to be equal because there are two third law force pairs acting. There's the one between the second block in the rope and the one between the first block in the rope, and the fact that the tension is constant throughout the rope. That's how we know that the magnitudes on the two blocks have to be the same, because you kind of have like, you have an associativity of tension, or of these third law pairs. Now the directions can change because of pulleys, and that's why they don't have to point in the same direction, but they are still the same magnitude. I know that gets messy. It'll get more clear when we see more examples. All right, so let's next let's talk about, come on, scroll for me, please. So there are two force pairs, yeah, but the point is because a rope is a simple thing, all we can do is we can just treat that, we just don't consider any forces on the rope at all, and we just treat the two forces on the blocks as pairs, as a third law force pair, and you just treat the rope as a conduit for those forces. So imagine that block 2 is pulling to the right on block 1, and block 1 is pulling up on block 2. All right, let's talk about contact and normal forces. I know that's tricky. We'll see a lot of problems regarding tension. There will almost certainly be a tension problem or a problem involving tension on the midterm. So get practice on these, and you will get practice. So the contact or the normal force is a balancer force. So what I mean by that is it provides sufficient force to prevent objects from passing through each other. Now, this might just seem like a fudge factor, and it kind of is, because right now, because we don't, like, with this explanation given, we don't really have an explanation as to where this force comes from. So the example here is you have your ground, you have your block sitting on your ground, a force of gravity acting downwards, and then you have a contact force. And I'm gonna, by the way, so for the most part, we will use F sub C, or we might have F sub, or we might have F sub N, or we might just have capital N. These all mean the same thing: contact force, normal force. So the point is if there was no force, if the only force acting on the block was the downward force of gravity, then by Newton's second law, that would mean the acceleration would have to be downwards of magnitude g. So the whole point of the contact force is it's there to be the thing that prevents the block from falling through the ground. If that wasn't there, the block would just fall into the ground, and we know that doesn't happen, which means that there must be a force that's holding it up. Mathematically, if the block is not moving, then that means, like if it's just sitting there, that means that the acceleration is 0. And so from Newton's second law, that would mean that the net acceleration, or the net force, is 0. So what does that say? It says that the magnitude of the gravitational force has to be equal to the magnitude of the contact force. Right? They have to be equal and opposite, otherwise there would be a net force. These are not third law force pairs, by the way. So the contact force is just there to make the acceleration whatever it should be, whatever we observe it to be. By the way, sometimes we might call this n as well. So the point of the matter is, or the point of all of this business, is that if the object is not accelerating, rather, if it's not accelerating perpendicular to a surface, then that means there is, or there will be, now let's say there is a normal force that ensures that the acceleration is 0, that let's say a perp is 0, where in this case a perp is just referring to the acceleration perpendicular to the surface. Now, is there also a contact force going down between the ground and the box as well? No. So there would be a contact force on the ground from the box that would be pushing the ground down, and that's just to say that, look, technically the box pulls up on the Earth with the force of gravity, right? So why doesn't the Earth just slide through the box? Because it's being pulled up, and that's because there's a contact force. Yeah, it's precisely that. Now, nowadays we actually do understand where this force comes from. It comes from a whole bunch of electrons in the ground, because it's made of stuff, and all stuff has electrons that are negatively charged. And then the stuff that's made that makes up the box also has a whole bunch of electrons that are negatively charged. And so if the force, or if the box were to try to overlap with the ground, the electrons would get too close. And we know that negatives don't like other negatives. And you'll learn more about this in 9C. But the point is the force that's actually keeping them apart is a force of opposites like charges repelling each other. And so that's the actual nature of the force that produces this contact force. But Newton didn't know about that. And you don't need to know about that to understand that a contact force is just the thing that holds things up. All right, so let's talk about another type of force. So the point is the magnitude of the normal force is generally not determined a priori. Like, it's not something that you can just calculate a priori. You have to know what the other forces are and what the motion of the object is. In this case, we knew that the magnitude of the normal force was mg, because the only other force that it had to cancel out was gravity, which has magnitude mg. If an object sinks into ground, it is overcoming this force, or something else happening, like quicksand. No, you're right. If an object is so heavy, then the normal force is just like the normal force, like we'll see with regards to friction. The normal force has a maximum as well. Like, it can be overcome. Usually what happens is it's overcome by pushing stuff out of the way rather than just squishing the electrons. But yeah, no, it can be overcome if the object is sufficiently heavy. Right, so the next thing to talk about is friction. So friction has two types, and we're going to talk about both. So there's static friction, and then there's kinetic friction. Someone outside my house? Oh no. Sorry, let me just, I think somebody's gonna show up at my door in a minute. Well, if they do, I'll answer the door. So let's talk about kinetic friction first. So kinetic friction is effectively the rubbing of two. Okay, I unfroze. Can everybody see me? So it's the rubbing of two surfaces. It's the force that makes two surfaces rough when they rub together. So it's the thing that makes it hard to slide sandpaper across wood, for example. So what's the direction of the kinetic friction? Well, the direction is in the direction that opposes the rubbing or the sliding motion. So the reason why sandpaper doesn't just glide across wood is because even though you're applying a force to the sandpaper to make it move, there's a friction that's pushing back, and so it makes it harder. So you have to apply a force in order to keep it moving. So so the force is in the opposite direction of the sliding of the sandpaper. If you stop the, hopefully this will work better. So we can also, so it's a force, so it has a magnitude and a direction. So what's the magnitude of the force? Well, there's a simple formula for it, and it's just an empirical formula. It's equal to the magnitude. So I'll write little f sub k. So this is the magnitude of the vector. These two things are the same. This is equal to mu sub k. So mu looks like kind of like a pointy m times the magnitude of the normal force, n. So mu sub k, this is a number that represents how rough the surfaces are. It has a name. The name is the coefficient of kinetic friction. It's not because it's overheating. All right, well, I'll do my best to continue. And then this n, this is the normal force. It's the magnitude of the normal force. And so if the two objects are being pushed together really hard, like think you have a really heavy object, then the normal force is going to be really large. So this normal force really tells us how hard the two objects are pushed together, or the surfaces are pushed together. Just as a note, n is the normal or the contact force. By the way, the reason it's called a normal force, I didn't mention this before, is that in mathematics, normal is often used to mean the word perpendicular. So it's perpendicular to the surface. Now, just as an important note, this equation here is not a vector equation. Super important. It's just an equation about magnitude. If you want to figure out the direction, you just have to think about the problem. You have to think about what direction is the motion in. Now, there's another type of friction, which is static friction. Did anybody ever end up showing up at my house? Oh, it was just the wind blowing. Okay. Not a big deal, right? Static friction. So static friction is like the normal force. Static friction is a reactive force. It's a reactive force that acts to prevent touching objects from starting to move. It acts to prevent touching objects from starting to move relative to each other. So this thing, this static friction, this is that whole business with inertia that we were talking about before. So when people say inertia, what they're really talking about is the magnitude of the static friction, or the maximum value of the static friction, that it's really big. That's why it's hard to get something moving, because the maximum possible static friction is large. Now, remember that the normal force will just take on whatever value it needs to be in order to prevent something from happening. But as somebody astutely asked, the normal force has its limits. Like if you push hard enough, then the normal force just gives way and the object will like sink into the ground. The static friction has the exact same thing, or has the exact same property. It's a force balancer in the same way. And so it will take on whatever value it needs to take on up to a certain limit. So the magnitude of the static friction, F sub s, is less than or equal to mu sub s times n. So it can be at most mu sub s times n, where n is again the magnitude of the normal force. This mu sub s, this is the coefficient of static friction. And again, it basically describes how rough the objects are. Like ice will have a very large or a very small coefficient of static friction. It's very easy to get something moving while it's on ice. But if you're talking about sandpaper, it will have a very large coefficient of static friction because it's hard to get something moving. So the point of this whole matter is that the static frictional force, it will equal the attempted pushing force in magnitude, will equal the attempted pushing force, putting that in quotes, until it reaches its maximum value. So its maximum value is mu sub s times n. And so it will equal that attempted pushing force. So it will match, like if you're pushing, it will match that force backwards until your pushing force is larger than its maximum possible value. After that happens, the object moves. The object starts moving. And then once it's moving, we completely leave the realm of static friction. So static friction is basically there until the moment the object starts moving, and then the static friction is zero. There's no more static friction. However, once the object does start moving, then the static friction transforms into kinetic friction. Now, the magnitudes aren't the same necessarily, but the friction that would have been, because it's no longer moving, it's not static anymore, or because it's no longer static, we just describe the motion and we just describe the force in a different way. We call it kinetic friction. So now let's try to answer the question explicitly. Why is it hard to slide heavy things? Let's do this like mathematically. So let's just draw up an example, free body diagram, sitting on something that's rough, make it rough and craggly so that it's clear that there's friction. So we have a downward force of gravity. We have an upwards force of the normal force, keeping it from falling to the ground. And then I'm just going to apply a pushing force to the right. And so if it starts out stationary, then there's going to be a frictional force to the left. Can you guys hear me? Well, this is still being recorded, so hopefully, so you can watch it if it's bad anyway. So now let's do the free body diagram. So, or let's analyze the acceleration. So the acceleration in the x direction, this is equal to F net in the x direction, and we're going to use, standard coordinates x and y, divided by m, which is just equal to the magnitude of the pushing force minus the frictional force, because it's pushing the frictional force is in the opposite direction. And so we know what so if this is zero, if the frictional force is preventing us from moving the object, that means AX is zero, which implies that the pushing force is equal to the frictional force, or rather that the frictional force is countering the pushing force. And so now let's think about this. So that means that the frictional force can take on a range of values, right? It can be from zero all the way up to some high value. So what's the maximum pushing force? Or how hard do you have to push to get this thing moving? Well, the maximum of the frictional force is mu sub s times n. That's the maximum possible value because it's always less than or equal to that. But from our free body diagram, this is equal to mu sub s, like n, the acceleration in the y direction is zero, so the magnitude of the normal force has to equal the magnitude of the gravitational force. So n is equal to mg. It's equal to the gravitational acceleration. And so what we have here is that in order to overcome this frictional force, you have to have your pushing force be at least mu sub s times mg in newtons. F push must be greater than mu sub s mg in order to push the I should put strictly greater than, in order to push the block. So what's the takeaway then? And by the way, we'll be done soonish, but remember, we are going to go a few minutes over because of the quiz. So what's the takeaway? That means that if the object has more mass, it will be, for a given frictional force, it will be harder to move because the normal force is larger, and hence the maximum value that the frictional force can take on is larger. This is why it's so hard to push. This is why, like, if you have like a 2 kilogram block versus a 50 kilogram block on the same surface, it'll be a lot easier to push the 2 kilogram block to get it moving than to push the 50 kilogram block. Also, this explains why it's so easy to push a heavy thing on a very slippery object, because if mu sub s is small, then it doesn't matter how heavy the thing is, you can just push it easily, because it's the important part is the product of the coefficient of static friction and the mass that matters. All right, so just as an aside, usually mu sub s is larger than mu sub k. That's just an experimental fact, and it should agree with your intuition. Typically, it's easier to keep something going than it is to start something moving. That it's a sensible. It's just a sensible guess to make, and it doesn't have to be the case. That's just usually the case for most surfaces. Now, the last force to talk about today, and then we'll probably end it here, is the elastic force. So the elastic force is like a combination of tension and a contact force. So the elastic force can push and pull, so tension pulls and contact pushes. And the elastic force is usually what we use to describe springs. So springs, the type of force that springs have, and hence what the elastic force is a restoring force. So when I say restoring, what this means is that if there's a deviation from the equilibrium, and I'll explain what I mean by equilibrium in a minute, if there's a deviation from equilibrium, then the force acts to return to equilibrium. So if you have a thing that's not in equilibrium and there's a restorative force on it, the force will push on the thing in the direction that it needs to go to be in equilibrium. And so this is encapsulated by Hooke's law. Hooke's law came about in like 1600s, it was really early. And it states that the magnitude of the elastic force is equal to K times the magnitude of delta X. Now this K here, this is the spring constant. So restoring forces apply to springs, as I said. It has units, unsurprisingly, of newtons per meter. And it basically tells us how stiff the spring is. So if the spring is really stiff, like if it's hard to stretch or hard to push, it will have a larger spring constant. This delta X, this is the distance that whatever object you're considering is from equilibrium. So let me draw a picture just to indicate what I'm talking about. So let's say you have a spring attached to a wall, assume there's no gravity. And if you just kind of left it there, the object would just happily sit at a particular position. We would call that position the equilibrium position. So when I say equilibrium, what I really mean is the position where the spring is happy to exist if it's not moving and if you're not touching it and there's no forces on it. So if we compress this spring, say to this position, then the delta x, the delta x that we were talking about is this distance here. And if we stretch the spring over here, then the delta x is this distance here. I should actually probably put that in brackets, or put that in magnitude, just that way then it's clear. Now, this is not a vector equation. So far, this just tells us what direction, what the magnitude is. The magnitude is just k times the displacement, times the distance from equilibrium, rather. And the direction is towards equilibrium. So the force on this one would be this way. It would pull the block back towards equilibrium. The force on this one would be to the right, towards equilibrium, and it would have the magnitude as specified by Hooke's law. Now, we can actually, we can actually write a vector equation. It's just a little bit trickier. So the vector equation that you can use is that the force of the elastic force as a vector is equal to negative k times the vector, and I'm sorry for doing this for overloading notation, but times the vector delta x. So this delta x here, this is like displacement that we saw before, but it's not final minus initial. This is, oh, what just happened? It's not final minus initial. It's either, depending on whether it's stretched or not, it's x, it's the position, it's the current position, minus the equilibrium position. So the point is in this case, you'd have to choose some coordinate system so that you could define these positions. But in this example, maybe we say that x equals, maybe we put our coordinate axes here. So this would be plus x, this would be plus y. And when I say, by the way, when I say x with a vector over it, that's really the xy position. So you might more accurately call this delta r. But just for consistency with what everybody else does, sometimes I'll use x as well. And then I'll write this as x current minus x equilibrium. So what we would have is that the, in this case, x equilibrium would be, I don't know, whatever this distance is, let's call it x naught. It would be x naught in the I hat direction. And x current, let's call it, would be, well, what would it be? It would be x naught plus the magnitude of delta x in the I hat direction. It's this much plus that much more, right, in the x direction. So then the elastic force would be negative k times x naught plus delta x minus x naught in the I hat direction, which is just simplifies to negative k times delta x in the I hat direction. So that would indicate that the force would point in the negative I hat direction, which indeed it does. So this vector equation, what it does is it accounts for the fact that that negative sign accounts for the fact that it points back towards equilibrium. And the reason for that is that the vector delta r points from the equilibrium position to the current position. So the vector, the force vector points in the opposite direction from the equilibrium, or from the current position to the equilibrium position. All right, so I'm going to end it there. Sorry for all the technical difficulties. Oh boy, Zoom just stopped responding.